All right. Good morning, everyone. So we'll get started. I just want to remind you guys that homework number 8 is due tomorrow. Okay, tomorrow by midnight. So make sure you finish them by tomorrow midnight. Okay, and the next homework will be up probably tomorrow at some point, and then it will be due a week from tomorrow. Okay, and that's going to be a Tuesday. And then for exam 3, this is my current plan. So you'll probably have exam 3 for the Friday lab attendees. That's going to be happen November the 6th, which is the Friday next week. Okay, and then for Wednesday's lab attendees, it's going to be Monday 2 weeks from now. Okay. So the reason I put again Fridays groups first is I plan actually to have them for the final. The Wednesday group will take the exam first. Okay, and then Friday group will take 2 days later for the final exam. Okay, so that's my current plan for right now. Okay. So today we'll start a new chapter on statics and torque. Okay, so there's a lot of scenarios when you see like a large rocks somewhere like in stationary. Okay, there's a chat message. Let me take a look. Right. So the question is about if we are online at that time, how will we take the exam? So I have thought about that. Um, so the academic affair is going to decide today, later today at some point, if we are going to continue online or in person. But and then that's probably like for the week from today to next week, and then they probably will redesign next week. That's my guess, but I'm not quite sure about that. But um, if we were going online completely for the remainder of the semester, then you guys will probably just take the exam online somehow. I need to explore the options we have. So Expert DA, I think I got email a couple of weeks ago, said there's options that they can have lockdown browser exam taken via Expert TA. So I haven't get a chance to explore that, but I will take a look on that. Okay. So if that's possible, then we are going to take exam online from Expert TA. Okay. All right, but yeah, we'll get to that point at some point later this week, um, or maybe early next week. Okay, but the bottom line is that you guys want to get prepared for exam 3. Okay. All right. So if you have object that is in equilibrium, okay, not moving in that case, so then the study of forces in equilibrium is called statics. Okay, so there's actually a whole new class on statics. Okay, a new course is on statics, which engineering groups students are taken. So that's basically studying forces in equilibrium, and that's for whole semester. Okay, but for general physics purpose, we will just use a chapter to have a basically concept on forces in equilibrium. Okay. So the first condition for forces, the object in equilibrium, that would be the net force equal to 0, because if an object is in equilibrium, right, it's not moving, then it's or actually there's two types of equilibrium. Okay, so there's static equilibrium, there's dynamic equilibrium. So static equilibrium, that means only the force is net force is 0, and then the static equilibrium means that both the net force is 0 and then the object is not moving. Okay, so it's two conditions for static equilibrium. The focus for this chapter will be static equilibrium. Okay, for dynamic equilibrium, the net force should be 0, but the object is not necessarily at rest. It might be moving. Okay, so let's take a look at that. The static equilibrium, the first condition will be net force is equal to 0. Okay, so if this is a two-dimensional problem, then you will have net force in x equal to 0. You will also have net force in y equals to 0. Okay, so both have to be satisfied. Okay. All right. And then so in the case of, say, static equilibrium, so for example, if the car is moving with constant velocity. Constant velocity, that means net force is also equal to 0, right? But in this case, it's moving, so it's not static equilibrium. It's called dynamic equilibrium. So in that case, net force should also be equal to 0. So in the x direction, the force, the driving force applied to the wheels, that should be equal to any resistance force that is on the car, okay? That they should cancel out. And then the weight of the car and then the normal force should cancel out as well, okay? So again, when you look at the forces in two-dimensional x and y directions should cancel out again, okay? So that's in dynamic equilibrium. Now, if you want the object to remain stationary, right? So net force is equal to 0. That's the first condition that has to be satisfied. But net force equal to 0 is not enough to keep an object from moving, right? For example, if you have two forces that are acting on the same object here, the hockey stick here, they are in opposite directions and having the same magnitude. So then from the free body diagram, you can actually move forces around so they are acting at the same point from the free body diagram point of view, okay? So it's not actually where the forces are acting at, but these two forces will cancel out, right, from free body diagram. But you can imagine that if forces are acting at different points, then this hockey stick will rotate, okay? It's not going to be stationary. All right, so then net force equal to 0 is not the sufficient condition for achieving static equilibrium, okay? So then must be another quantity that is in equilibrium or cancel out that had to maintain the object in equilibrium, okay? So, um, so for that quantity, let's take a look on the second section here. So imagine if you are tightening a screw, okay? So where do you want to apply the force? At the very end of the screw of this, what do we call this? Yeah, I don't, yeah, wrench, okay, yeah. On this very end of the wrench or very close to this end of the wrench. Now you can do both, right? You can try both. So you'll figure like you need less force if you're at the end of the wrench right here, right? But you need much larger force if you are close to here, right? So that tells you that the distance to where this guy is rotating, on the nuts is rotating, that matters, right? So R matters, and then F. So it looks like R times F. Okay, if you have larger R, then your F is smaller. If you have smaller R, then your F has to be larger, right? So it looks like the product of R and the F has to be a constant number in that sense, right? Also, if you are pushing on a door over here, if this is a revolving door, so you know that if you are pushing on this end close to the X rotation, then you need larger force, okay? And then on the further end, you need actually less force, okay? So basically, this quantity in terms of the distance from where the force is applied to the X rotation, and then the magnitude of force, it's called the torque. Okay, torque is defined as R times F if R and F are perpendicular to each other. Okay, and the SI unit, and then we use symbol. This symbol looks like T, but it's actually called tau. Okay, tau is equal to R times F. The SI unit comes from Newton, comes from R, that's the length, and then F comes from Newton comes from F, force, and meter comes from R. Okay, so Newton times meter. So torque increases as the force increases, and then also the distance as the distance increases. Okay. All right. Now, in general, you might apply force that's not perpendicular to R, right? R is from the X rotation to where the force is applied, so that's R. And force you may be apply in this direction, right? So if you apply in this direction, for example, if you are in the playground, if there's a merry-go-round, if you try to apply force in this direction, the same direction as R, then actually the merry-go-round will not move. Okay, so that means you actually apply zero torque. Okay, But if you are applying the force F, that is having an angle with R, that's theta, okay? So then you can move this guy merry-go-round to start to rotate, okay? So you actually will take this component of the force, which is perpendicular to the R, okay, and then times the R, okay? So torque is going to be equal to F. The component, the force component that component is in the perpendicular to the R, okay? So that's what you take, that component. This component will do zero work, okay? The force component in the same direction as the R will do zero work. So basically, in general, if you have an angle that is theta between R and F, then torque is equal to RF sine theta, okay? So this is in general the definition, RF sine theta, okay? And you can actually rewrite this guy, right? So you can do F times R times sine theta, okay? So you can do it this way. You can take the component of R that is perpendicular to the F. So the same way, um, then you can do R sine theta times F to be the torque, okay? So if you do that, then R sine theta is called the it's called the lever arm. That's its R with a perpendicular sign. That means the lever arm, okay? So that's the component of R that is perpendicular to the force, okay? All right, so let's take look at one example here. So this one says, at one position during its cycle, the foot pushes straight down with 440 Newton force on a bicycle pedal arm that is rotated an angle of 65 degrees from the vertical. If the force applied is 0.17 meters from the x rotation, what torque is produced? Okay, so it basically gives you the R and also gives you the force and then the angle between the two, right? This angle phi is the angle between the two. So it's asking you what's the torque, okay? I probably can give you guys a couple minutes and be just straightforward applying equation of RF cosine or RF sine actually, okay? And then we can take a look on the solution together in a couple minutes. All right, so let's take a look here. So it gives us that this is R, and then this is where the force is applied, and then gives this angle phi. Okay, so you want to be careful about the angle here. So this, in this case, this is the angle will be the same as this one, because this is straight downward, this is parallel to this guy, right? So then these two angles are the same. So basically it's going to be just RF sine of phi, okay, in this case. Then you can plug in the numbers you are given for the quantities. Sine of 65 degrees, okay, then that's equal to 67.8 newtons per times meters. Okay, so this is your torque straightforward over here. Sometimes in a problem you are given an angle, but that might not necessarily be the angle between R and force. Okay, R and F vector, so then you have to be careful about that. But in this one, yeah, the problem is nice to you guys, so it gives you just the angle there. Okay, all right, let me know if you have questions on this one. All right, if that's clear, then we'll move on here. So for torque, actually it's a vector quantity. So it has a direction. Okay, so um, this is how the direction has been defined for torque. So similar to the angular displacement, or the angle is defined, the direction for angle. So if you have a force that is making the object rotate counterclockwise, then that torque is positive, okay? Or making it having a counterclockwise angular acceleration. If it causes the clockwise angular acceleration, or just imagine, just look at that force only, and then see what direction will that force make the object rotate. Okay, so if it's going to be clockwise, then it's negative. Okay, so in the figure shows here, there are two forces. One force is pulling the wheel in this direction, and then one force is pulling it in that direction. um, so then torque by this guy, you're going to just ignore that one, just focus on this guy, right? So then it's going to move the wheel rotate counterclockwise. So torque by this guy will be positive. Now torque by this guy, you're going to ignore this force. So then torque by this force is going to make the wheel rotate clockwise. So then the total torque should be torque by this one minus torque by that one, because this one is positive, this one is negative. Okay, this one will give you a negative torque, this one will give you a positive torque. Okay, all right. So then for an object to be in static equilibrium, then this is the second condition, that net torque should be equal to 0. Okay, so chances are you are going to have like multiple forces on the object. Okay, so then you have multiple torques due to multiple forces, then the torque should add up to be 0. So then the object will be in static equilibrium. Okay, so two conditions: net force equal to 0, net torque equal to 0. All right, so let's take a look on the second example of the day here. So it says two children push on an opposite sides of a door during play. Both push horizontally and perpendicularly to the door. One child pushes with a force of 17.5 newtons at a distance 0.600 from the hinges, and the second child pushes at a distance of 0.45 meters. What force must be this must the second child exert to keep the door from moving? Assume friction is negligible. Okay, so again, I'll let you guys work on this one first, and then probably like about 5 minutes or so we can take a look on this together. Okay. All right, so let's take a look here together here. Okay, so I have a top view from the above the door to see this scenario over here. So on this side it's the hinge side. So then the door will rotate on with this the X rotation the rotation going through the hinge side of the door. Okay, so one child is pushing with 17.5 newtons force, and then that's a point 6 meters away from the hinge. The second child is pushing on this here 0.450 meters away. So it's asking what's this guy. Okay, so um, so if they want to achieve equilibrium, that means the door is not moving, right? So they want to keep the door from moving. So then these two, the torque by these two should be equal to each other, or they should add up to be zero. Okay, so torque by F2 is going to make the door go in counterclockwise direction, right? By F1, it's going to make it clockwise direction. So then torque by F2 will be positive, torque by F1 will be negative. So the condition will be net torque equal to zero, right? Net torque will be from these two. So it's R2 F2 minus R1 F1. It's going to be zero, okay? Because by F2, the torque produced by F2 should make the door going counterclockwise direction. So that means R2 F2 equals to R1 F1. Okay, so you're looking for F2, then you divide both sides by R2. Okay, so 0.600 meters multiplied by 17.5 newtons divided by 0.450 meters. Okay, that will give you 23.3 newtons of force. Okay, that's how much force need to be applied. Okay, all right. Any questions you guys might have? Okay, so if you guys are all clear, we will move on. Okay, so then for static equilibrium, both net force should equal to zero and then net torque should be equal to zero. Okay, so that's the two conditions for static equilibrium. So for example, the figures here for two children sitting on a seesaw. So there's for the seesaw and the children as one system, there's this weight, and then there's weight of this child, there's weight of this child, and then there should be the supporting force from the pivot point to the seesaw going up there. Okay, so then those three forces should add up to be zero. If you take upward to be right the positive direction, then this force minus this guy should go to zero. Okay, now you can see the whole system will be rotating about this pivot point over here. So then net torque should be equal to zero. So net torque is going to be coming from the weight of this child times R1. So W1 times R1, it's going to make the seesaw go counterclockwise direction, so positive torque. And then for the girl here, it's going to make the seesaw go in the clockwise direction, so negative. Okay, so W2 R2 negative. Now for this force, okay, because this is the pivot point where the x rotation, so R for this force is going to be zero. Okay, so then this force will produce zero torque, so that's not in the second equation because it's zero. Okay, so then you have net torque equal to zero. Okay, all right. Now so if a problem you have a system that is in static equilibrium, then the net torque should be, it's going to be zero. Okay, so for example here, so you can see there's not necessarily a clear indicator of which point will be your x rotation, right? But if net torque is going to be zero for the system, then the x rotation can be chosen as at your choice. Okay, so you can choose that this point to be your x rotation, or you can choose this point to be your x rotation, or maybe anywhere from the middle. Okay, now the rule of thumb is you want to choose where the x rotation, um, where the force, there's force at that point, exert at that point, or better that there's multiple forces at that point. So then when you calculate the net torque, because that's where the x rotation, so the force acting at that point will have zero torque. Okay, and a lot of times if you have an unknown force, you can also pick that as your x rotation, so then you can solve for the other forces. Okay, so just keep in mind, if net torque is zero, then choices of x rotation will be arbitrary. Oh, you can actually pick any point to be your x rotation. Okay, so um, for example, if you have a light fixture over here, so let's this steel part or whatever material that might be that is fixing this guy. Okay, so there's be tension on that point, there's this fixture point over here, there'll be force over there. Now for this force, you can resolve it into x and y direction. Okay, and then there's weight of this light itself going in that way. So there are three forces. If you resolve this forces into the components, then there are four forces over here. Okay, so then in x direction, forces should add up to be zero. In y direction, force should be add up to be zero. Okay, now you can actually pick this as your x rotation, so then you can solve for t. Okay, if the weight is given, or you can take this as your x rotation, then this force can be solved. Okay, so either way. Okay, but if this is two-dimensional problem, then you can actually get two equations from net force equal to zero. So in total, you are going to have three equations. Okay, so net force in x direction equal to zero, that's one equation. Net force in y direction equal to zero, that's the second equation. And then net torque equal to zero, that's the third equation. Okay, all right. So let's take a look on this one here. So this one says a 65 kilogram person stands on a lightweight ladder as shown in the sketch. The floor is rough, hence it exerts both a normal force F1 and a friction force F2 on the ladder. The wall, on the other hand, is frictionless. It exerts only a normal force F3. Using the dimensions given in the figure, find the magnitude of F1, F2, and F3. Okay. So you want to apply net force in x direction equal to zero, net force in y direction equal to zero, and then net torque equal to zero. Okay. I think it indicates that pick this as your x rotation. Okay. So I will have you guys give it a try, then we can take a look at the solution together in a few minutes. Okay. All right, so let's take a look here. So as I mentioned, both conditions for static equilibrium should apply here. So then net force equal to 0. Okay, that means net force in x direction is equal to 0. Net force in y direction is equal to 0. And then net torque is equal to 0. Okay, so from this guy, net force in x direction, so you can see there are two forces in x direction. So F2 in the positive x, F3 in the negative x. So you can write F2 minus F3 then equal to 0. Okay, so that's your first equation. Net force in y direction should equal to 0. So F1 is in the positive direction, mg is in the negative direction. So F1 minus mg, that should go to 0. So that's the second equation you can have. Now, because the system is in static equilibrium, so that means net torque should be equal to 0 because it's not rotating, right? So you can pick any point to be your x rotation. In the figure, you indicate you can pick this point as your x rotation because there are two forces here. So then R for both forces will be 0, so you can get rid of two torques by picking the x rotation over here. You can of course take the other points as your x rotation here or there or anywhere in between. That should be fine, but because this one has two forces, this point has two forces on acting on it, so it's most convenient to take that as your x rotation. Okay, so then torque will be coming from this weight and then this guy. So for this guy here, it's going to in that direction. So this is the x rotation. So this is force. This would be the lever arm. Okay, so that's called A in the figure here. So A is equal to 3.8 meters, and then this is called B, that is 0.70 meters. Okay, so then torque by F3 will be F3 times this A. All right, so or A times F3. That will make the ladder go counterclockwise direction. Minus mg, okay, if you draw this way down, so then this is the 0.7, actually that's the 0.7, just up to there. Okay, that's where the 0.7 is. So this is perpendicular, this r is perpendicular to that force. Okay, or this is the component of r perpendicular to the force. So then that's your lever arm. So B times mg, that goes to 0. So you have those three equations. Okay, you have three equations, you have three unknowns. Okay, but these three equations are actually easier ones. So because this is equal to that, so then F2, you can see that F2 will be equal to F3, right, from the first equation. And then from the second equation, you can directly calculate what's F1, because second equation tells you F1 is equal to mg. Then it's the 65 kilogram times 9.8 meters per second square. Okay, that will give you your F1. It's going to be 637 newtons for F1. Okay, now to solve for F2 and F3, because F2 is equal to F3, so then you can turn to the third equation over here. Okay, so the third equation, A is given as 3.8 meters times F3 minus B as 0.70 meters times mg. Mg will be F1, right? Mg is the 637 newtons. That goes to 0. Okay, you can solve for F3 here. So basically, this minus that is equal to 0. That tells you this is equal to that. Okay, 3.8 meters times F3 equals 2.7 times 637. Then you divide both sides by 3.8 meters. And that will be your F3. So your F3 is going to be equal to 117 newtons. Okay, that's F3. And then also F2, because F2 equals to F3. Okay, so you have solved all those three forces. All right, any questions you guys might have on this one? All right, if you guys are clear, we can move on. So I figure we have extra time. I just add a few slides over here. So let's check on the next section. All right, so next section talks about stability. Okay, so we know that you can have object in equilibrium, right? For example, you can have this ball in a curve like this. Okay, so this is a value over here. So if you move this guy, the ball to like one side, and it has a tendency of going back if you remove your force. Okay, but so then this, for this equilibrium, it's called stable equilibrium. Okay, because if there's a disturbance over here, disruption of the position over here, then it will come back. But on the other hand, if it's over here on the top of the curve over here, then if you push it to either side, it's going to be just roll off, right? So this equilibrium point is not, it's not stable. It's called unstable equilibrium. Okay, you can also have a scenario like this. So this is neutral equilibrium. Okay, so for a system, if you have multiple masses in a system, then the system can be equilibrium at a pivot point called the center of mass, or in some textbook it's called the center of gravity. I think in this textbook it's called center of gravity. In some cases they are called it's called center of mass. So either center of gravity or center of mass, they are the same. Okay, so for example, if you have two masses over here, if this being is having negligible mass, then the center of mass for this two can be found by putting a rope over here. So if it can be equilibrium at that point, then that's the center of mass. Okay, you can kind of move this around to see where that can be balanced. So then that's the center of mass. Okay, and in mathematically, you can write equations for center of mass, position of center of mass. If this is one dimensional, you can say the x position for the center of mass, that should be equal to m1 x1 plus m2 x2 divided by m1 plus m2. Okay, or capital M, which is m1 plus m2. So basically, the mass of one object times its x position plus the mass of the second object times its x position, and then divide by the total mass. You can calculate the center of gravity by using the equation. Okay, if you have more than two objects, then you just add up the mass times position for the rest of the objects up on the numerator, and then put the extra mass in the denominator here to sum up for the total mass. Okay. All right, let's take a look this example over here. So this one says a 0.34 kilogram meter stick balances at its center if a necklace is suspended from one end of the meter stick. The balance point moves 9.5 centimeter towards the end. Find the mass of the necklace. Okay, so let's say there's a meter stick over here. Now there's a piece of information here hidden. It says meter stick, right? So that means this guy has a length of 1 meter. Okay, so there's something hidden here, but it's given. So this is 1 meter or 100 centimeter. Okay, now it says it can be balanced at the center point initially. Okay, so center point, which is halfway at the middle. Okay, now it says if you add a necklace to one end, so it doesn't specify the left end or right end, so you can either put it either way. Okay, so it doesn't really matter. So let me just put it on the left end over here, so a necklace over there. I'm going to call the mass for the meter stick as M1. So M1 is 0.34 kilogram. Okay, and then we are looking for M2, the mass of the necklace. Now it says if you put a necklace over here, then the balance point, which is the center of mass, moves towards the end. Okay, so moved over here by 9.5 centimeter. Okay, so this is new center of mass. All right, now let's see. We can actually set up the, so we can pick up where your origin is for. This is one dimensional, right? This is in x direction. The position for the meter stick is in the horizontal direction, and then also for this necklace is also there. Okay, so we can pick, you can pick anywhere, but I'm going to pick the center to be the origin of my x coordinate, and then towards the right to be the positive direction. Okay, again, this could be arbitrary. You can pick here, all right, you can pick there, doesn't really matter. Okay, so now in this case, this is my center of mass, right, in this coordinate system. So my center of mass now is equal to negative 9.5 centimeter, because let me stop sharing so you guys can see a larger window on your end if you click speaker view. Okay, so my center of mass now is minus 9.5 centimeter. Okay, so for x1, it's going to be this guy, right? It's going to be 0, where my origin is. For the meter stick, it's center of mass over there. For m2, x2, then it's equal to, so this is 0. On this end should be 50 centimeter, right? Because 1 meter stick is 100 centimeters, so minus 50 centimeter. Okay, so I can set up the equation that x center of mass for the whole system should be equal to m1 x1 plus m2 x2 divided by m1 plus m2, right? I know this guy, I know m1, I know x1, I know x2. So the only unknown in this equation will be m2. So I should be able to solve for m2, right? Now, before I'm doing anything else, I realize that x1 is equal to 0. So this term actually goes away. Okay. So now, to solve for m2, you have m2 over here. You also have m2 over here. So you want to multiply both sides by this guy, or move this guy to the other side of the equation. So m1 plus m2 x center of mass, that's equal to m2 x2, right? So you're looking for m2. It's on both sides of the equation. You want to isolate them. So this guy you want to distribute inside there. So m1 x center of mass plus m2 x center of mass equal to m2 x2, right? You want to move m2 to the other side of the equation and then isolate that. So m1 x center of mass equals to m2 x2 minus m2 capital X center of mass. All right, so then this is m2 x2 minus x center of mass parentheses m1 x centimeter center of mass. All right, so then after doing that, I will divide both sides by x2 minus x center of mass. Okay, x2 minus x center of mass to solve for my m2. All right, I have everything here. So m1 is 0.34 kilogram times x center of mass minus 9.5 centimeter divided by, okay, x2 will be the minus 50 centimeter minus 9.5 centimeter. Okay, so that will give me 0.0798 kilogram, or roughly 0.080 kilogram if I keep 2 digits for everything. Okay, so once you have the right equation set up, so then a little bit tedious on the algebra, but it's kind of straightforward. Okay, just be careful about, like, from one step, moving from one step to the next one. Okay, let me know if you have questions on this one. All right, so if that's clear, we'll move on to the next slide over here. Okay, so if the object or the system is a two-dimensional system, then you want to find the center of mass in x direction and also in y direction. Okay, so you will have just repeat the center of mass equation twice. Okay, so one in x direction, one in y direction, pretty much the same. All right. So x center of mass then equal to m1 x1 plus m2 x2 divided by m1 plus m2. Y center of mass is equal to m1 y1 plus m2 y2 divided by m1 plus m2. Okay. Now you can also expand this into three-dimensional. So then z center of mass should be m1 z1 plus m2 z2 divided by m1 plus m2. Okay. All right. So a lot of times, if you have multiple objects in a system, you also want to just represent the velocity for the system, treating it as if it's at the center of mass. So you'll be just looking at the motion of the center of mass. Okay, so then for the velocity at center of mass, it's going to be similar to the equation for the position center of mass position. So it's going to be m1 v1 plus m2 v2. Okay, divided by m1 plus m2. And keep in mind, velocity is a vector quantity. So if this is 2D, then you can explain it to two-dimensional as well. Okay. All right. Lastly, if you have an irregular shape object, okay, so for example, the US map, if you have a map like maybe made in wood, so you want to determine where's the center of mass. Okay, so to determine the center of mass for the irregular shape object, okay, one convenient way is to hang the object, okay, with the rope at one point, and then draw a line that is going through the rope, the vertical line. And then now pick a different point, hang the object again, and then draw the vertical line through the object. So when these two vertical lines intersect, that's where the center of mass, okay? Because center of mass should be following on both the vertical line when you hang them at different locations. So then the intercept will be the center of mass, okay? So that's one way to determine it, okay? All right, so I think we'll stop here for today. Okay. Um, yeah, I just realized. So if we are going to go online totally, then for the exam we will not separate the two groups. We'll just take the exam at the same time. Okay. So that's just another note for the exam. But we'll see about that probably like later today, and then throughout the next week some point. Okay. So that will be it for today. All right. Okay. I'll see you guys in lecture again on Wednesday morning. Okay. See you guys.